So, we all learn about Newton's laws of motion in school, right? They're supposed to be these fundamental rules for how everything moves. But have you ever looked around and felt like the real world just doesn't play by those rules? Well, today we're going to dig into that. We're going beyond the textbook to look at the powerful, invisible forces that don't break Newton's laws, but actually help us master them. These are the forces that literally shape the world around us.
And it all starts with this simple little puzzle. Think about it. Newton's first law, the law of inertia, is pretty clear, right? An object in motion is supposed to stay in motion forever unless some other force messes with it. So if that's true, why does a book you slide across a table grind to a stop? Why doesn't it just, keep on sliding? It feels like a paradox, but it's not a flaw in the law. No, it's actually a massive clue, pointing us towards a much deeper understanding of how things really work. So, to figure this all out, we've got to go back to square one. Let's do a super quick recap of the basics. We're going to step into Newton's perfect, idealized world for a second. The one from the physics problems with no friction, no air, just the pure, clean rules of motion. Okay, so first up, you've got the law of inertia. That's the object in motion one at the heart of our little puzzle. Then there's the big one, F equals m, the absolute powerhouse equation that connects force, mass, and acceleration. And of course, the third law. For every action, there's an equal and opposite reaction. These three, they're like the holy trinity of classical mechanics. This is our fundamental toolkit. And yeah, in a perfect world, a total vacuum with zero friction, this toolkit is flawless. It predicts everything perfectly. A satellite coasting through deep space, it's going to go forever, just like the law says. But, and this is a big but, down here on good old Earth, things are, well, they're a lot messier.
But you know what? That messiness is where all the really cool physics happens. Our everyday lives are just packed with examples that seem to totally contradict that perfect model from the textbook. It's almost like there are some missing pieces to the puzzle, right? Some extra rules that only apply here in the real world.
And this chart here really breaks it down. See, in your physics textbook, you push something, and that's the only force. It just keeps going. But in real life, oh no, there are always these other forces pushing back, fighting against the motion, and that changes the whole equation. The net force, that's the force that actually matters for predicting movement, isn't just your push, it's your push minus all that resistance. So that brings us to the million-dollar question, doesn't it? What are these invisible, always there opposing forces? What is this resistance that's causing all the trouble and bridging the gap between our perfect theory and messy reality? All right, let's meet the two main culprits. I want you to meet friction and drag. These are the forces that fight back. They're the reason that books stop sliding. They're the reason a car has to keep its engine running on the highway just to stay at a constant speed. These two are everywhere. So let's talk about friction first. The easiest way to think about it, it's like the universe has a built-in braking system. It's this force that pops up anytime two surfaces try to slide past each other. It's the grip between the book and the table. It's the grip between your shoes and the floor. And hey, it's not all bad. Without it, you literally couldn't walk. You'd just be slipping around all day. And then there's drag. Think of drag as friction's close cousin. But instead of happening between two solid things, drag is what happens when you move through a fluid. And here's a fun fact. To a physicist, the air all around us counts as a fluid. The perfect example? You know that pushback you feel when you stick your hand out the window of a moving car? That's drag in action. Now, this quote right here, this gets to the absolute core of what we're talking about today. And this is so important. Friction and drag don't break Newton's laws. They are applications of his laws. We're not throwing out F equals ma. We're just getting more sophisticated about what goes into the F part of that equation. These forces aren't an exception to the rule. They are part of the rule. They're an essential part of the whole system. Okay, so enough with the theory. Let's see how this all plays out in the real world, where the stakes are incredibly high. We're going to look at an engineering challenge where getting a handle on the force of friction is, and I'm not exaggerating, a matter of changing people's lives. What we're talking about is a total hip replacement. I mean, this thing is a modern medical marvel, for sure. But when you strip it all down, it's a pure physics and engineering problem. The central question is, how on earth do you build an artificial joint that can move smoothly, day in and day out for decades, inside a person's body? And if you're an engineer on this project, your checklist is daunting. First, the joint has to handle some serious forces every single time you take a step. But here's the kicker. It has to do all that with as little friction as possible. Why? Because too much friction means things wear down, it creates debris, and eventually the whole thing fails. The entire design process is basically one big war against the force of friction.
The solution they came up with is just elegant. It's a super polished metal ball that replaces the top of your femur bone, and it rotates inside a custom-made cup. Simple enough, right? But the real magic, the secret weapon in this whole war on friction, it's all in the material they use for the inner lining of that cup.
Okay, pop quiz time. Let's see if you've been paying attention. Why did they use that special plastic-like material for the lining? I mean, why not just go with a super polished metal ball inside a super polished metal cup? Metal on metal, that sounds pretty strong, doesn't it? Go ahead and pause for a second. Really think about it. Okay, you got your answer? It's all about absolutely crushing the force of friction. It turns out even perfectly polished metal on metal creates a ton of friction. They just grind each other to dust over millions and millions of steps. But that special polymer material, it creates one of the smoothest, lowest friction surfaces we can engineer. It's what allows for decades of smooth movement. It is a total masterpiece of applied physics.
All right, let's wrap this all up. Let's put it all together. We started with Newton's perfect, ideal laws. And then we added in the messy, real-world forces. And what we end up with is a totally new and way more powerful way of looking at motion.
So here's your practical takeaway. Think of it like a physicist's checklist for any real-world problem. Step 1, you always start with Newton's fundamental laws. Step 2, you put on your detective hat and you find all the forces acting on the object. And I mean all of them, your push, gravity, and you absolutely cannot forget to include friction and drag. Once you have all of those, then and only then can you calculate the real net force and figure out what's actually going to happen. And really, that's the big idea here. Friction and drag, they aren't just annoying little details your teacher throws into a homework problem to make it harder. They are fundamental, essential forces of nature. And understanding them, being able to predict them, and best of all, control them, well, that's how we engineer our entire world, from life-saving hip joints all the way to super efficient airplanes. So we've spent this whole time talking about friction and drag as the bad guys, right? The forces that slow everything down. But here's a final thought to leave you with. Can we ever use them to our advantage? Are there times when these forces are actually our friends? I'll let you chew on that one. Thanks for joining me.